pipeline that we usually take for granted. On the educational side, enrollment is falling. Financial aids systems are struggling, and more students simply disengaging from schools. That's not just an education story. It's a sign, it's a signal that the supply of future skills is under stress. At the same time, the AI narrative has shifted from cool new tools to entry-level work may disappear, especially white-collar roles that used to be the first step into the middle class. And then there is mobility that I know majority of you are interested. Immigration rules and students' flows are changing. It means that the global talent pipeline is tightening just as the demand for adaptable skills is rising. So what is the question? The question that I want to start with is simple, not to answer, but by nature. If the value of skills is shifting this fast, who can pivot and who gets stuck? That is what I'm trying to measure: education, exposure, career path, and the forces that associated with adaptability. Well, everyone talks about adaptability, reskilling, AI proofs a skill, talent retention, etc. But we don't actually have measurement systems that follows skills across these different life cycles. Education research tells us about programs, how the programs look like. Labor research tells us about the outcome of the education. AI exposure work tells us about which skills are affected. And migration research tells us about where talent goes. The problem is these are disconnected body of literature, and my research is trying to build a linked pipeline across 4 junctions so we can measure adaptability at a scale and study who benefits, who gets displaced, and how the institutions reshape the global talent flows. To connect them, we need data, lots of data. In my work, I'm using many data sets, including 10 million course syllabi, more than 600 million LinkedIn profiles, administrative data sets, academic publication, and many more. Let's start with the classroom. Education is one of the crucial contributing factors contributing to economic growth and social progress. In general, people with a college degree have a higher chance of earning more and having more extensive professional networks. Well, that sounds good news, right? The following question is one of the main questions that motivates my research. Have the opportunities and threats toward the college-educated workers remained the same, consistent over the past years? Let's consider artificial intelligence as an example. Almost a decade ago, Frey and Osborne found out that college-educated workers are less automatable. This finding is mainly due to the creative nature of the work, of the task required in their workplaces. They concluded that it seems unlikely that occupations requiring a high degree of creative intelligence will be automated in the next decade. A decade after the previous study, a science paper by OpenAI scientists and Daniel Wright from UPenn analyzes how LLMs like GPT-4 might reshape the US labor market. The paper established exposure scores by combining human expertise and GPT-4's workplace task assessment to determine the job alignment with LLM capabilities. Unlike the previous AI studies, this paper shows that the college-educated workers, mainly us, are the most exposed to automation from LLMs. For the first time, generative AI specifically threatens to automate or provide opportunities for college-educated workers by altering a skills requirement. So, which skills colleges providing to the student as they prepare to enter the workforce? We know that the graduates' earning and mobility ability outcome vary across different majors and type of institutions. The common naive approach to investigate such difference is using abstraction above the skill level, including a worker's college major, their alma mater, or their current occupation as the only source of information. On the other hand, there is a strong body of literature demonstrating the benefits of modeling jobs as the bundle of skills and task requirements. Skills matter for modeling the future of work, but where do the workers get those skills? Let's depict the problem through an oversimplified figure. On the left side, we can see a high-level representation of the skills that a person learned during their studies. On the right side, we can see some examples of occupations along with their required skills. As a human, we are able to map the graduate first to computer scientists, then biologists, and finally, maybe agricultural engineer. But how to automate this procedure? Building a framework to automate this procedure is challenging due to two main reasons. First, it is not easy to understand the process of a skill acquisition. Second, what should be considered as a skill? First, let's tackle the problem of a skill definition. Since the long-term goal of my research is to identify how skills taught during college education relate to the labor market outcomes, we use the ONET database maintained by US Department of Labor. ONET is an ontology of workplace skills, abilities, and tasks that they use to describe every occupation in the US economy. Most importantly, the ONET is used by labor economists and policymakers as a single standardized way to represent work in terms of skills. It has been used extensively for understanding and analyzing the labor market and workforce. So I will use it in my research as well. For those of you who might not be familiar with the ONET, it is composed of various taxonomies. For example, abilities with nearly 50 elements provide the most abstract classification of the skills, and task statement with nearly 18,000 elements provide the most detailed representation of the skills. In the rest of the presentation, for simplicity, we had a discussion about it. I refer to these taxonomies as the skills. The first contribution of this work is developing the syllabus to ONET, a framework for extracting ONET skills from course syllabi. Let's see how it works. To put it simply, the framework receives a raw syllabus as input. It applies some natural language processing steps to produce a vector representation of the syllabus in the ONET space. Basically, each value represents the semantic similarity between the syllabus and the given skill. To put our framework into practice, we use the data set provided by Open Syllabus Project, OSP for short, which provides more than 3 million course syllabi from more than 3,000 US universities for over 20 years. As a second contribution, we apply our framework to the millions of syllabi that I just mentioned, extract the ONET skills from them, and we made Course Skill Atlas dataset publicly available. Let's start with a face validity check of the syllabus to ONET framework. Here, we list the 10 DWAs, 10 skills that are most strongly associated with two example fields of study: biology and computer science. Some DWAs, such as prepare informational or reference materials, are common across many fields of study, and therefore they shadow the DWAs that most distinguish one field of study from the other. To normalize for this, we use the technique called RCA. Basically, it's similar to TF-IDF if you're coming from computer science background, that helps us to understand which skills are more unique to that field. For instance, research disease or parasite is predominant in biology, and coordinate software or hardware installation is leading in computer science according to the RCA score. Here you can see how different fields of studies are connected based on the skills they teach. We looked at the DWA to see which fields have the most overlap. For example, physics and chemistry have a strong similarity because they both focus on technical skills. On the other hand, fields like marketing and economics are connected because they emphasize business and analytical skills. What is really interesting is that we can see two big groups, one for somehow technical fields like STEM, and another one for more humanity-based fields. But there is also some crossover. For example, film and photography, which we usually think as an art field, also teaches technical skills like designing video games. What it shows us is this shows us that the education is becoming more interdisciplinary with skills blending across different fields. Now is the time to see some examples of utilities of the course skill atlas that we just produced. For the first time, our dataset gives us a way to directly compare the skills taught in higher education with those needed in the labor market. To build the labor force skill profile, we use national employment data from the US Bureau of Labor Statistics and then compare them with the skills we identified from the course syllabi. What we found is that across all fields of study, the skills being taught are becoming more aligned with what is needed in the US job market. This might suggest that higher education is adapting and teaching skills that are future focused, or the market is becoming, the graduates go and shape the market. It can be both sides. But that's not always the case. Also, we can focus on a specific field of study. For example, a specific market and a specific field of study. For example, when we look at computer science syllabi, compared to the skills needed for computer and mathematical occupations, the data shows that over time, the labor market skills are diverging from older course syllabi. This probably reflects how quickly these fields are evolving, and it highlights the challenge of keeping academic programs up to date with industry changes in these specific fields. Also, we can use this data set to study demographics. For example, when we look at the enrollment data for men and women, we see some clear trends. Healthcare-related skills like prescribed medication are more common among women, while engineering skills like design industrial processing systems are more common among men. When we compare abilities between these two genders, we find that women tend to develop fewer numeracy skills and more literacy skills compared to men. And all of these things are based on the enrollment. Our dataset also allows us to explore how skills change over time within different majors and universities. Take social sciences, for example. There has been criticism recently that active learning in this field focuses too much on new methods and overlooks important skills like reading, listening, and taking notes. The suggestion was to find a balance between newer and traditional approach, but they couldn't really measure this trend. We did it. By looking at social science syllabi, we tracked skills like written comprehension, written expression, and oral comprehension. What we found, well, as you can see here, these skills, writing, reading, and listening, are actually on the rise with a steady focus over the years. So where is the problem? Active learning, as one of the researchers, Ishiyama, describes it, it is all about the students doing more than just listening to a lecture. It's about getting involved and using different techniques to stay engaged. When we looked at the skills related to active learning, we found time sharing the most relevant one. It is the ability to manage multiple things at once. That is a key part of active learning. But here is the issue. As we can see, time sharing has a negative slope, and it is being removed from the teaching material over the years. Maybe that's the answer to the concern of the other researchers for this matter. Now let's talk about money. Research has consistently shown that there is a strong link between what you major in, the skills you learn, and how much you earn later on. To put it simply, we use, again, the same RCA score that I just introduced, and we are tracking how much unique skills you learn during your study. And as we can see, it correlates with your with the income. And we tested over different RCA cutoffs. I tried to show you some utilities of this data set. Now, what we can find using this platform, this data set that we created about AI education and labor market. Public debates often pins worsening job prospects in AI-exposed occupation on one moment, the release of ChatGPT in late 2022. The story is basically LLMs went mainstream and displacement follows right away. Here I test the timing. If ChatGPT is the main driver, we should see a clear shift after late 2022, after the launch of ChatGPT. So the central question is simple. Did AI-exposed jobs start deteriorating before or after ChatGPT? To investigate this crime scene, we combine course skill atlas that we just developed for measuring the AI exposure in education with more than 10 million career profile obtained from LinkedIn profiles to track graduates and the job, to track graduation and the job start, and monthly unemployment insurance to capture labor market outcomes. Putting them together gives a single timeline to see when things start to shift. But how about the exposure to AI? As discussed earlier, a science paper established the exposure paper by combining human expertise and ChatGPT self-assessment to determine job alignment with LLM capabilities. Basic exposure essentially captures the extent to which a specific task of a job could incorporate or be straightforwardly assisted by LLMs without requiring significant change to the nature of the task. For example, examples of tasks with an exposure score equal to 1, a complete exposure, include administer online purchasing systems or analyze and maintain data logs for audiovisual activities. And the tasks like acquire, distribute, and store supplies or adapt other designers' ideas for mass market have 0 exposure score. Unlike Frey and Osborne, they found out that the tasks of educated workers are more exposed to LLMs. It is really important to note that we should not interpret, at least at this stage, exposure as a good or bad thing. We don't know yet. What is unemployment insurance risk, or UI for short? We estimate the UI risk as the probability that a worker in a given occupation and a state claims regular unemployment insurance in a given month using counts of insured unemployed from administrative data provided by BLS. It is computed as the insured unemployed count divided by insured unemployed count plus the number of employed. How does it help us? Here we can see that unemployment risk from unemployment insurance claims by LLM exposure. In a simple comparison of the most exposed versus least exposed occupations, more exposed occupations were often less often risky before the ChatGPT. But around early 2022, that advantages started to disappear some months before the release of ChatGPT. When we split occupations into 5 exposure groups, you can see the same thing happening here. The higher exposure groups start to drift above the lower exposure ones, and the separation begins again before ChatGPT is released. Now let's focus on the recent college graduates and ask how the early career market changed around LLM exposure timeline. We use resume data here to answer this question. Why? Because it lets us observe people's first job after graduation and the timing of the job start. The thing that we cannot see and are not available, at least clearly, in most administrative data sets. For example, graduates probably didn't have job to apply for unemployment and they have a previous occupation. As a result, it is somehow impossible to use administrative data for this analysis. In panel A, we compare graduates whose first job is highly LLM exposed to the graduates highly exposed to others in the same graduation cohort. Before 2022, they tend to start sooner, but for the 2023 and 2024 cohort, they start later. Panel B runs the same idea for high salary first jobs. Delays increase after 2022 as well, which tells us part of what we are seeing is a broader early career slowdown, not only exposure. And by looking in panel C and D, they track who gets which job month by month after graduation using job gap. Basically, it asks whether a cohort's share of job start in a given exposure group is higher or lower than what you expect based on that cohort's overall share of all job start that month. Simply, positive means overrepresented, negative means underrepresented. Finally, in C, that is the most exposed job, the 2021 and 2022 cohorts are underrepresented early on, and that dip starts months before the launch of ChatGPT. However, in panel D, that is the least exposed job, you don't see the same pattern. But the question is, should universities teach AI skills? Here, I connect what graduates learned in college to how their first job search played out. And I asked whether LLM exposed training became more valuable after ChatGPT or not. I built an education exposure score by matching the syllabi to the science paper LLM exposure that we discussed, and then linking them to the outcome, that is a starting salary, the left side, and months to first job, right side. The key term here is the interaction with the post-ChatGPT period. After December 2022, graduates with higher educational exposure see higher starting salaries and shorter time to their first job. They spend less time for finding job. Even after controlling for local job opening and reset of fixed effects and so on and so forth. When I also account for how LLM exposed the first occupation is, the pattern points to complementarity, if I want to interpret it. LLM aligned training helps most when the job itself relies more on those tasks, meaning that if you have high exposed training and you find high exposed job, it will help you in the market. What are the main takeaways from this part of the analysis? First, the idea that ChatGPT single-handedly disrupted the labor market is too simple. The initial downturn in AI-exposed jobs started earlier and lines up with broader economic shifts. Second, LLM-relevant education still looks like an asset. It predicts higher salary pay and faster placement in the post-ChatGPT period. Till now, we've learned something important, that the shock isn't just a single product release, and the people who do better aren't randomly distributed. The education that complements LLM era task still pays off, but those patterns still leave a deeper question unanswered. When the value of tasks shift, who can actually pivot and who gets stuck? So the next step is to stop treating the labor market as a set of occupation and start measuring career path. That's where we need a way to map how close different roles really are, how options expand or collapse over time, and how a person's past experience shape their feasible moves and why. Because that's what turns something like exposure, that was a shock that we discussed, into adaptability. To do so, I developed the career space. Career space is a learned map of career where distances reflect how people actually move between roles. Basically, we start with raw resume timelines, and we do some important data preparation. Each step becomes a short text string like software engineer at Google or information science degree from the University of Pittsburgh. And from that point, we turn consecutive steps into observed transitions, that is, all positive examples. And we create negative examples by pairing sources and destinations that do not appear as real. Then we fine-tune one of the language models here, Sabet. So real transitions get high semantic similarities, and fake ones low semantic similarity. The output is career space that is an embedding where we can score compatibility between roles and predict which moves are plausible. To put it simply, we teach the model what the frequent careers are and what are the unlikely moves. Here I'm comparing a generic Sabet embedding, that is our base model, the base of our model, to career space after fine-tuning on real resume data. On the left side, we can see the base model that mostly groups things by entity families. For example, all universities are clustered together, all industries, US state, all of them are clustered together. For example, something like Cornell University and Cornell College that necessarily do not have that much mobility between them are really close to each other. On the right side, we can compare, we can see career space that is built on actual mobilities. Here, universities, firms, and occupation that show up in real paths cluster in the same neighborhood, while others will pull apart. Again, you can see some examples here. Since there are not that much mobility between Cornell University and Cornell College, they will become far away from each other. The main point is that the career space turns semantic similarity into something closer to mobility similarity. Question. Let me share some preliminary results with you that we can do with this model. Still, it is a part of the work that is ongoing, and don't take them fully for granted. Many robustness checks are needed. Among the many possibilities here, I turn career space into trajectory-based measure of compatibility. To put it simply, for each person, I embed their career history, compare it to all occupations available in the job market, and get compatibility profile that is how many realistic options they have, how close you are in all the available options in the market. I also add a simple decay rule so compatibility can persist but fades over time as well. The left figure links average written compatibility to 35 owned skills, skill measure across several estimators. The right figure groups skills into 7 categories, just to have a better, to avoid the correlation and better interpretation. And the result become much more stable and easier to interpret, showing which broad skill bundles are most associated with having more visible options in the occupation space. The preliminary analysis shows categories associated with systems-oriented and social complex problem-solving skills tend to load positively, make you more compatible, and resource management and content are negatively contributing to your compatibility to the different occupations. Well, career space lets us measure how people's options expand or narrow as their career unfolds. But when options change, people don't just switch roles, they might switch places. Some stay, some return, some move on, and those choices quietly reallocate skills across countries and different locations. So the next question is, when talent moves, who gains, who loses, and how do institutions shape those flows and their innovation consequences? Competing for talent takes more than high salaries. It also takes social conditions that make careers and life sustainable. Women are an increasing share of the high-skilled workers, but when women empowerment is low at home, returning often comes with a real career penalty for the talented immigrants. That turns brain drain into a persistent outcome. Talents leave and the pull to come back is weak. In that sense, empowering becomes a mobility layer when opportunities and protections are constrained. Staying in the US for work or PhD become the higher option choice because the alternative narrows what is feasible. What we do here to investigate this part of the problem, again, we turn into the data, we combine LinkedIn career histories, the variety of democracy, women empowerment indicators, and SciSciNet publication records to study nearly 2.6 million skilled immigrants who came to the US to track their mobility decision and their scientific outcomes. When are women more likely than men to return home? As we can see here, in low women's empowerment origin countries, skilled women immigrants return less than men. But as women empowerment rises, the gap closes and eventually flips. So at higher empowerment, women become more likely to return than men to home country. We just saw the row pattern that I showed you. The female minus male return gap depends on women's empowerment, and it can even flip. But that was a binned comparison. So here I tighten up the results by adjusting for other factors and separating different cohorts of immigrants if they come first time for a study or work to the US. You can see the return probabilities rise with women empowerment for everyone, but that line for women rises more steeply, especially among those who came to the US for work. The main point here is that the empowerment doesn't just raise return overall, it changes the gender gap in who returns. We just saw that women empowerment shapes the who returns. The next margin is human capital investment, specifically whether immigrants pursue a US PhD or not. Because pursuing a PhD leads to a longer stay, more time in the country, and increases the chance of staying in the host country. Here I show that the PhD pattern is also gendered and shift with empowerment in the reverse of staying, but the same concept. As we increase the women empowerment score, less a US PhD becomes less interesting for immigrants. Up to now, we have talked about who returns and who pursue a US PhD. The last piece of the puzzle adds what is at stake: scientific output. In panel A and B, you can see that immigrants, even those who go back home, publish substantially more than comparable non-immigrants. And higher women empowerment is linked to higher output overall. Finally, panel C gets to the brain drain margin here, that stayers publish more than returnees, and the difference is specifically costly when women's empowerment at origin is low, because that's where women are less likely to return and face the largest productivity penalties relative to men. And as the last slide, to briefly explain where I stand and what is my research agenda moving forward. How does it look like? I'm in favor of technology, but we need evidence. We need to know where AI works, where it doesn't, and for whom it works the most. The main goal of my research is to identify which occupations grow or shrink with firm AI adaptation and which tasks drive the shift. The key concern to me is the training pipeline disruption that is happening, and one of the desired output for me, ideal to me, is a monthly public dashboard on task value, displacement risk, and education job alignment. And please let me finish the presentation by introducing our lovely lab, Morgan Frank, my advisor, Ching, Arezu, and Wendy, that some of you are gonna meet them in NetSci. Thank you.
Questions? I have a lot. Okay. Yeah.
Very nice presentation.
Thank you.
Can you just explain again how you calculate the skills? I think that you're calculating skills so that they can be linking both the syllabus and also the ONET.
Okay. A skill, I use ONET as the taxonomy. For example, programming is one of the skills in ONET, but it doesn't distinguish between Python and Java. Both of them are the same. Then I take the taxonomy, 18,000 skills, tasks from ONET, and I have the syllabus. Then I use the semantic similarity in the language model to understand how similar each syllabus is to each of these skills.
And do you calculate the similarity based on how many skills ONET skills are mentioned in the sentence?
In fact, I take each of them and calculate the cosine similarity between the string of that skill with the string, with the text of the syllabus. Yeah.
Thank you for your talk. Can you please repeat one of the last points about the difference between stayers and returnees? Is that for number of publications, you said?
Yes.
So what was the result? Stayers publish more?
Still, if we want to compare the stayers versus returnees, still stayers, the immigrant who come to US and stay here publish more than the ones who return back. Meaning that if I go back to my country, probably I will publish less compared to the others. If I stay here, I publish more. Yes. Yes.
I have a question about, I think that regression table that you have about happened with some AI exposed or LLMs exposed jobs. You found that they take more time to find a job, the jobs that are exposed to AI, right? 2 months more.
Yes.
So do you have a tip? You can bring back
yes.
the table back.
Just I'm hearing an echo. I don't know.
I think this is the crucial table for most of us came to the top to know what we have to do, right? So this is crucial because it shows that still people that are exposed to AI are going to win more money, right? But this is changing. It's actually the gap between people which are, I remember Morgan showing us these plots in which the salaries of people that are, for example, software developers are going down, while health workers, for example, is going up. So the gap is actually getting lower, but it still is larger for software developers than from health.
Yeah.
So the table is showing that, exposure to LLM is actually, you take more time to actually find a job, and then you get more salary, but still you have more salary. So it's
yes,
right?
Yes.
It's not that the jobs are disappearing completely, and it's not that people are not going to get salary.
And let's say that you have two, let's keep the program fixed. Computer science, you have two universities, A and B, I don't name. A teaches you more LLM exposed skill than B. Considering the current result, there is a higher chance, no causal claim, that you will spend less time in the job market and hopefully will have a higher salary. Yeah.
Questions? I have another one, which is about, go ahead.
So, in the research about women empowerment, said if the women empowerment is high, then women are more likely to return back to their country.
Yes.
Did you see that women empowerment was maybe correlated with economic factors?
Thanks for bringing it up. That's a really good question that you asked. Actually, we did it. It is highly correlated, but where was it? Here you can see we controlled for residualized GDP. Actually, women empowerment is correlated with GDP, but we residualized it. As a result, that's a pure GDP in there without correlation.
think some of in the Neuroscience Institute, some of us are looking at the scientific output and how scientific output of the neuroscience is related to other universities here in the context. We compare ourselves. This is the typical exercise. So you have the syllabus and how much the syllabus of different universities match the labor market. Do you see that there's a difference regionally? We are proud in Northeastern of this experiential AI or the experiential learning, that we have a different type of syllabus that our friends on the other side of the river. So do you see that there's a competition between skills or a difference, a complementarity of skills between universities that are in the same region?
Region, yes, if you can. I can share something with you. Back up a slice, the best ones. This is coming from one of the old work, but for example, this is I combined on region based on the syllabi that is coming. For example, Arizona and Florida are the most exposed fields, states in the US.
I mean, the syllabuses are...
Yes, but I haven't controlled for the biases. There can be, I have to control for many things. For example, probably there are many fields, yes. It is driven by fields, yes, definitely.
I was thinking more about competition, I mean, locally. Like, for example, in Boston, you have 10 universities.
I promise to do this this analysis specifically. So yeah, and we'll send it back to you.
Measure the experiential learning.
Yeah.
Okay, more questions for Ali? Yeah. Well, thank you so much, Ali, for your time.
Thank you. Thanks for having me.